Thank you very much. I'm Andrea Bolzoni. I'm a PhD student at the Open University. My supervisors are Professor Robin Laney, Dr. Alistair Willis, Professor David Sharp, and Dr. Adam Linson. My research project is on a machine learning approach for timbral exploration in free improvisation. And today I'm going to talk about one of the components, one of the aspects of my research. So to give you a little bit of context, I have developed and I wanted to investigate to what extent an interactive reflexive musical system could support musicians, improvisers in exploring timbre music making or timbre-oriented music making, where interactive reflexive musical systems are defined by Pache as the class of interactive systems in which users can interact with virtual copies of themselves. And I identify timbre music making as I mentioned before, in the context of free improvisation. And really, like if you think about, let's call them extended techniques, or really any sound you can produce with, musical instrument or an object or whatever. And from a theoretical perspective, there are some similarities to the concept of spectral morphology. So the question that I'm going to talk about today, that is a sub-question of my research project, is can a model generate variations of a timbre-oriented musical phrase using a small data set and in a small amount of time? So the context is, again, an interactive music system. And I had to assume that musicians would want to explore music material without having a huge amount of data they could use to train a model. So at the beginning, sorry, it's skipping up a slide. Oh, okay. It's not my laptop, so there might be some mixing of slides. So sorry, at the beginning, I consider using audio descriptors. So I considered, well, I can extract some audio descriptors from sounds, and I can tweak them and then generate variations. But the problem was that I didn't want to focus on a specific set of sounds or on a specific instrument, so I didn't really have a way to select a subset of audio features. So I decided to investigate unsupervised methods, and I ended up using a vanilla adversarial autoencoder. And this led me extract some features. So if we go through an example, you can see here the spectrum of a sound that I'm going to play in a second. So I produced this sound on a guitar with an E-bow on a string on which peg was bouncing. And using an adversarial autoencoder, I was able to reduce compress, let's say, or to represent the spectrum you saw before on these three-dimensional space. So what you see here are the 3 dimensions on which the 513 beats were compressed. So what I have here is a sort of representation of the spectrum. And once I was able to obtain this representation, I could transform the latent space and generate some variation. So what I wanted to do was to use some trajectories or morphologies or shapes that were already included in the original sound. So I experimented at the beginning with a very simple technique. I took one of the dimensions. You see here in the dark blue, the first dimension, and I flipped it. I reversed it on the time axis, on the horizontal axis. And once I had this transformed latent space, I could generate the spectrum, and from the spectrum, I could generate the audio. So here it's not a massive variation because the sound space, I call it, I started from was not very different, but there is a variation. So again, as you might see where I'm going with these, once I do the transformation, apply this transformation one dimension, I can apply to all the other dimensions. So this is the second latent dimension flipped, and this is the spectrum, the transform spectrum on the right, and this is the sound. And again on the third latent dimension. So again, these are not massive changes, but what I showed so far is that starting from an audio sample on the top left, I can generate these three variations with this simple transformation on the latent space. It becomes more interesting if we consider that this sample was taken from a longer phrase. We were listening to the fourth segment here on this phrase. This is a 15-second phrase, and the red lines represent a segmentation that I computed on the novelty curve. So I'll play for you the whole phrase. And of course, what I can do now is to apply this transformation on each segment separately. So here is the transformation, the flip transformation, as I'm calling it, on the first latent dimension segment by segment. And again, of course, I can apply it to all the latent dimensions, but I can also change the granularity of the segmentation. So applying this transformation segment by segment will produce, again, a different variation of the initial phrase. And again, there's no need to play these, but again, of course, I can apply other, change the granularity of the segmentation again. So what I showed is that, to go back to the initial context, is that I can have a musician playing a short phrase to a system, and this system can, using a simple transformation on a latent representation, can produce a number of variations and throw them back to the musician. Now, what happens next in the segment, in the interaction, is out of the scope of this segment, of this presentation. But I mentioned at the beginning that I wanted to train, to be able to train a model quickly on a small amount of data to use these in an interactive context. So the phrase we've been listening to is a 15-second phrase, and the training on a GPU, it takes just 30 seconds, and the generation time goes between 12 and 11 milliseconds, depending on how many segments you have, which makes it really suitable to be applied in a interactive music system context. And these are the references, and yep, thank you.